Good morning, everybody. This is Derek Harp, the founder and chairman of CSA, and I'm real excited that you've all chosen to attend our webcast with one of our top and early supporters, Waterfall. As you know, CSA is a not-for-profit, a 501c6 organization, and we largely our budgets are established by supporting companies, and Waterfall has been was one and still is one of the very first sponsors to ever sign up, and then has consistently been supportive in many ways beyond just the financial underwriting that our organization needs from companies, also supplying us with expertise and advice and help in launching specific projects. And this is the more than we can ask from any of our SAPs, and we really appreciate Waterfall's leadership in that area since the origin of our organization. And clearly we have other companies that we're grateful to as well. And we're always looking for additional companies. If you want to get involved, there's more ways than ever to support and be involved and be recognized in helping the world's largest peer-to-peer networking educational opportunity for the workforce focused on securing industrial control systems. We are still growing all over the world. There's an organic nature to this. It's clearly a topic of great interest. We've passed 16,000 organic registrations, and at the rate that is continuing, will be over 18,000 before the end of the year. So it's exciting, and we continue to just try to figure out how can we serve the needs of people all over the world that are wrestling with the issues around the security of these sorts of systems. And it is a ubiquitous problem no matter what country you're in, and obviously in some places there are less resources than others ready to to try to tackle this particular problem. So it is our mission to try to help everybody. A rising tide will lift all boats, and we've got the opportunity to do that. And one of the ways we can do that are these amazing virtual educational series that we now do. And we've got an amazing brain trust of individuals involved on the Global Advisory Board and as chapter presidents and as speakers and as SAPs, which I'll introduce one of those folks right now, a veteran of the space. So how can we take all of this knowledge gained by people who have been working on this problem longer than anyone and translate that to value for everybody, walk away learnings? And today is one of those examples. We have another one coming up at the end of the month with another long-standing, hardworking, well-known person in the space, Steve Mustard, who has worked in and continues to work in some of the largest automation environments, gas and oil specifically, but I think others as well. And he'll share some of his share some critical information about the Mission Critical Operation Professional certification. So I hope you can attend that. And during the webcast, please definitely input questions into the question bank. You'll notice in GoToWebinar, there is a pre-made form over in the tool for inputting questions, and we will try to get to those questions at the end of Andrew's presentation. But go ahead and put them in along the way. That gives us a chance to review those and kind of be thinking about them prior to Andrew finishing the formal part of his presentation, and then we can queue those up and get into the specifics that you want to get into. And you've got a great person to do that with. If you don't know Andrew, and I'm assuming many of you do, this is another one of these veterans who, there aren't that many people who've been working on this problem. When you start measuring in terms of decades, it's a small group of people. And Andrew is also the author of a couple of books. His latest one is this Secure Operations Technology book you can see in the right-hand corner. And you can get it on Amazon, but also as a strategic partner for CSA, he will make it available to our members and to people participating in our events, so you can reach out to him. Actually, he'll share, I think, at the end of his presentation, a way for you to get your hands on his second book that has come out. And so I recommend that you definitely take advantage of that. So without any further ado, what I would like to do is introduce Andrew Ginter, VP of Industrial Security at Waterfall Security Solutions.
Hello, Derek, and thank you for that very kind introduction. And hello to everyone, and my thanks for joining us. Give me a moment here mechanically to switch presenters. And Can you see that, or is my GoToMeeting in the way? There we go. So my topic is secure operations technology. This is the topic of my new book. Let's just launch right into it. Here we are. Lots of people talk about IT/OT integration. In reality, though, there are not two kinds of networks in industrial enterprises that we need to worry about. There's three. There's IT, there's OT, and there's engineering. And credit where credit is due. You know, this third network here is not my insight. I was introduced to this way of looking at the problem very recently in an interview with Joe Weiss. That interview is on the Waterfall Industrial Security podcast, and I hope it's going to be published Monday. I've got more information on the podcast on the very end of this, so hang on if you're interested. But let's talk about the three networks. The big difference between these networks is physical risk. IT networks have business risk as, in a sense, a worst case consequence. OT networks, the big consequence people worry about is downtime, plant downtime, trip to plant, and now who knows how long it takes to come back up. And occasionally, you know, there's concerns about IP theft as well. Engineering networks, we're concerned about lost production, yes, but more importantly, we're concerned about damage to very costly equipment. We're concerned about worker casualties at the site. We're concerned about public safety and, you know, preventing environmental disasters. So the scale of consequence is increasing here, and the nature of consequence is changing between the IT, OT, and engineering. The IT consequences are typically business consequences. The OT and the engineering network consequences are increasingly severe physical consequences. What's the difference? Well, you know, if the bad guys get into our enterprise networks, in the NIST framework terminology, we detect, we respond, we recover. Respond and recover looks like identify the affected machines, isolate them, erase them, restore from backups, and repeat. The problem with OT and engineering networks is this: if a refinery or a power plant goes down because of a cyber attack, we can't restore lost production. We can't restore damaged physical equipment or human casualties from backups. The unacceptable physical consequences here means that we need to be very reliable on these OT and especially the engineering networks. Change is the enemy of reliability. Every change risks causing a malfunction. Complexity is the enemy of reliability. Systems that are too complex to, you know, for the human mind to understand, and it doesn't take much to get that big, we start losing our ability to confidently predict the safe and, you know, physically reliable operation of those systems. What does that mean for security? Well, antivirus signatures change constantly. Well, that's change. That's a threat. Security updates are even more extensive changes. So that's a problem. Encryption is complexity. It makes everything harder to understand. And again, the deeper we go from, you know, IT to OT into engineering, the more that becomes a liability in terms of, you know, keeping everybody safe. And so what it means is that, you know, the enterprise approach of, you know, some aspects of the enterprise security program, meaning constant aggressive change to stay ahead of the bad guys, we cannot apply that to the OT and especially the engineering networks. And so if an enemy gets into those OT and engineering networks, well, they are soft targets. They are soft interiors. This is why we see opposition from operations. This disconnect between the enterprise security and engineering needs. You know, the operations people will resist applying the enterprise security program because it's a threat. This confuses a lot of people. A lot has been talked about here. It's, you know, it's not that anybody is getting it wrong. It's that there's a disconnect that we need to understand here, and we need to do something about. Increasingly, we're, you know, at Waterfall, we see IT teams becoming truly responsible for OT security, And this resistance results in paralysis. Things just aren't happening that urgently need to happen. So what's the solution? Well, in terms of the modern parlance, it's called microsegmentation. What is microsegmentation? Well, to an enterprise network architect, the enterprise wide area network looks like one large and, as much as we can make it, homogeneous network. I'm sorry, IT teams are chronically underfunded. The only hope we have of meeting our mandates is standardization. Reduce the inventory of technologies we have to learn, reduce the number of spares that we have to maintain, reduce the number of vendors we have to negotiate agreements with, simplify by standardization. Inside this corporate WAN, there may be, there's sites. Inside the sites, there may be different kinds of networks. We tend to firewall everything on the enterprise WAN. We tend to connect everything to a homogeneous set of Active Directory controllers. We standardize as much as possible. And I've said all this, so I'm going to move ahead. What we're recognizing, though, is that nothing's quite that simple. Even in the enterprise space, forget the industrial space, there are exceptions. The set of virtual machines that implements the SAP server is enormously important to the business. It tends to be microsegmented and protected more thoroughly than the average enterprise asset. The set of virtual machines that is serving web applications out to the internet is exposed to attack in ways that the rest of the network is not. And so it also tends to have a more robust microsegmentation strategy and a set of special security rules applied to it to make it more robust. So there's precedent for some deviation from the enterprise standard, generally in the direction of becoming more robust. More robust because certain networks are more important. So what does this mean? The little networks of safety instrumented systems are enormously important. They're part of the safety system. They're designed to protect human life, to prevent casualties at the site, to prevent disasters. And so microsegmenting them in a robust way, in a more robust way than the average enterprise asset, especially because the interior of these safety systems is intrinsically a soft target, makes sense. In a lot of enterprises, protective relays are the same thing. These are small computers that look vaguely physically like the safety computers, but they're designed to protect large assets, $300 million turbines or, $10 million high voltage transformers. And so again, they're managed for physical risk. Engineers manage these things. It makes sense generally to say these are the most important physical consequences. Microsegment them and, improve the security as much as we can, given that there's a soft interior. And in fact, downtime for a large plant, if we have a $100 million physical plant, physical asset, and an intruder gets in and trips the plant, it can take days to come back to full production. Sometimes it takes weeks. This is a huge cost. And so often what we'll see is microsegmentation of entire control systems. The most important control systems, be they safety systems, protective relays, or outright control systems for important physical assets, we see being microsegmented and managed as engineering assets, not as enterprise assets. How do we figure all this out? Successful enterprise security teams sit down with their operations counterparts and figure out where to draw the line. Which assets are important enough to protect as engineering assets using the engineering change control discipline, and which of them are enterprise assets that are to be managed and secured as pretty much every other asset in the enterprise. The methodology that we see the most thoroughly secured industrial sites use to manage engineering chain control networks is this. The name is new. You know, I invented the name, but what I did was when I wrote the book here, I tried to give a name, a common set of names, a common set of terminology to the perspectives, the practices, the methodologies that I observed in thoroughly secured sites that have figured out this enterprise and engineering and OT difference. So I call it secure operations technology. The fundamental difference in perspective is that on enterprise networks, we seek to protect the information, the CIA, the AIC, the something of information. On OT and especially engineering networks, what I observe is that we seek to protect physical operations, to protect the engineering assets from information. Because after all information is a potential attack. All cyber attacks are information. Every piece of information can be an attack. And so we focus on protection from information in these engineering assets. Now, the Black Book has been called controversial. But really, all I do in it is I document the practices of the high end of the bell curve. I document what I see these secure sites actually do. To me, this is not controversial. This is good reporting. To me, what I think should be controversial is that I don't see anybody else talking about these practices. I don't see anyone else documenting what the world's most secure sites do. And what they do is really quite different from what the average site, so the bulge in the bell curve here, does. The thing is that cyber attacks are only becoming more sophisticated. Cyber attack tools are only becoming more powerful. The physical consequences that we observe as a result of these attacks on control systems are only becoming more severe, these consequences. And so all of us are strengthening our security posture. On the bell curve of security posture versus, number of sites, the entire bell curve is shifting to the right. This is how we respond to this increasing threat in the environment. The entire bell curve is shifting in the direction of the world's most secure sites. And there's not enough people talking about what these sites do, hence, my desire to write this book. A big part of the discipline for securing engineering and OT networks, the important control networks, the ones with unacceptable physical consequences of compromise, a big part of it is perimeters. Now, the IT gurus will tell us the perimeter is dead. Where's the perimeter around our cell phones? Where's the firewall? Where's the guards, gates, and guns? There is none. How much important business information is on the cell phones? Well, an enormous amount, typically. And they're right. The perimeter is dead on enterprise-type networks. But if you think about every important industrial site any one of us has ever visited, there's a fence around it, isn't there? There's guards, there's gates, there's guns, there's locks. You might ask, what is an important site? How do you define important? If it's important enough to build a fence around, it's important enough to have a cyber perimeter as well. A physical perimeter and a cyber perimeter go together. There's always physical perimeters around important sites. So once an enterprise has defined their important sites, they've defined the assets within those sites that have unacceptable physical consequences. We call those assets, those groups of assets, even groups of control systems, groups of networks. We group them all into what's called control critical networks. Once we define the control critical networks, what we do is we inventory information flows. Again, all cyber attacks are information. So a complete inventory of information flows into control systems is nothing more or less than a complete inventory of all possible attack vectors. With a list of all possible vectors in hand, secure sites, they go about blocking or disciplining those attack information flows. Secure sites not only control and discipline, whenever possible, they use physical protection from information. They don't trust software. I mean, software has a role. Software security systems have a role, but fundamentally, all software has bugs. I mean, I wrote software for 25 years. I didn't try to put bugs into my software, but in spite of the best efforts of me and all of my colleagues, in all of my career, everything we produced had bugs in it. Some bugs are security vulnerabilities, discovered and undiscovered. And so in practice, all software can be hacked, even security software. The people that we see working at the high end of the bell curve, the most thoroughly secured sites, they say, we're supposed to use security software, using vulnerable security software to protect vulnerable control system networks. It smells a lot like bailing a basement with a bottomless bucket. It's fun to watch, but it's really frustrating if you need to see progress. We want to get rid of frustration. They use physical protection as much as they can. They use conventional enterprise security programs, as much of them as they can as well. Now, there's a couple of exceptions. I talked about antivirus and such. They use as much of those programs as they can, and they layer SecOT on top of that to produce an even more robust program. Now, there's only two ways for attack information. A perimeter. Attack information, any information for that matter, it can move online or it can move offline. Offline means it's carried on a cell phone, on a USB key. It's physically carried in the head of an attacker. Chapter 4 in the book is all about protection from offline information and attack flows. For example, removable media, wherever practical, glue shut your removable media ports. Use an antivirus scanning kiosk for all inbound media. Something like the OpSWAT or the Honeywell Secure Media Exchange system. Scan any incoming drive. You deploy these systems at the physical perimeter. The security guard on the way in says, do you have any drives? Scan the drive. And files that pass the scan that you need to bring into the system, you copy to another medium. You pull a known good USB key or CD drive out of a stack beside the kiosk. You copy the good files, and you scan these files typically with between 4 and 8 antivirus engines. But you scan them, you copy the good stuff to a known good media. You carry it 3 feet to a file server. You load this stuff on a file server, and as much as possible, use the file server to distribute that within the control critical network. This is an example of controlling offline information flows, disciplining offline information flows. For complex flows like antivirus signatures or software updates, we do not take them straight into the control system, thank you. We take them onto a test bed. The test bed is instrumented for threats to safe operation, threats to reliable operation, and for security threats. The test bed is not just to check will the software operate correctly. It's, in a sense, a big sandbox that we're using to see if anyone has buried a nasty inside of complex information artifacts like code coming in. So that's chapter 4. Here's an example of something new. A lot of these protections here in chapter 4 are going to seem reasonably familiar to enterprise practitioners. Here's an example of something new. It's a cyber near miss protocol. In a lot of physical processes, we have safety near miss protocols. If someone observes, I don't know, a 3-ton object being winched into the air, and a person with a hard hat on walks under the object, walks through it, and 10 seconds later the thing falls to the ground, that's a safety near miss. If circumstances had been just a little different, if timing had been just a little different, we'd have a casualty at the site. You write these things up. They get analyzed at the end of it. They get aggregated, summarized, analyzed at the end of the month, and we prioritize remediation. Same thing with cyber. Every alert that goes to the SEN from the industrial system gets written up as a cyber near miss. At the end of the month, we discover that 39% of the cyber near misses were because Andrew kept using a USB key. Someone needs to go and give Andrew remedial training. So, this is something we're seeing emerge at industrial sites. Online controls, when it, so the offline controls seemed reasonably familiar. We might have applied them more intensely than we see them applied on enterprise networks to control incoming information flows. With offline controls, the nature of the offline controls is fairly dramatically different from the nature of online controls. I'm getting my onlines and offlines mixed up. Online, wireless, wired, firewall, this kind of continuous communication flow is very different in SecOT. How SecOT forbids firewalls between control critical networks, engineering or OT networks that are managed as control critical, forbids firewalls between them and non-critical networks. The only online communication that's permitted at the sites we observe, at the sites I've documented, use unidirectional gateways. They replace at least one firewall in the layers of firewalls in a defense depth architecture. They replace at least one of those layers with a unidirectional gateway. What is that? For anyone not familiar with it, this is the NIST definition, NIST 882 definition of a unidirectional gateway. It's hardware in the center here, hardware that's physically able to send information in only one direction. There's a fiber optic laser on this circuit board. There's a receiver on this circuit board. There's a short piece of fiber. You can send from one to the other, from the industrial network to the enterprise network. There's no laser on the receive circuit board. It's not physically possible to send any signal back into the industrial network. All cyber attacks are information. No information gets back. No attacks get back. It's that fundamental. But it's a combination of hardware and software. The hardware is physically able to send in one direction. The software makes copies of servers, like databases or OPC servers, or emulates devices. And everyone on the enterprise network who needs the industrial data interacts bidirectionally, normally, with the replica servers. And they have all the data they need in the replica servers. Nothing ever touches physical operations. Chaos can consume, ransomware can consume the enterprise network. The operations network is blind to whatever's happening out here. It can take days for the chaos to be subdued on the enterprise network. The power plant, the lights stay on. Gasoline keeps coming out of the refinery. The railway system keeps moving. Trains do not run into each other. This is the nature of the one-way connection. But you might ask, how does this work? I mean, a lot of people find this very confusing. The HMI network needs information from the PLC network. The historian network needs information from the PLC network. The HMI network needs information from the historian network. How can this work? A lot of these communications seem fundamentally bidirectional. The key is that the control critical network needs to be defined very carefully. We define it so that the control critical assets and even industrial control system subnetworks are completely contained inside the control network. They might use firewalls internally. We see a lot of firewalls used in control critical networks for internal segmentation. But at the edge of the control critical network, where we connect to the non-critical networks or the non-control critical networks, that's where we see the unidirectional communications. Now, that's fine in theory. In practice, there's always something that has to get back in to control critical networks. What do we do? I mean, look at the sort of the leading edge, the bleeding edge of industrial control systems. It is the industrial internet, the industrial internet of things. Well, I am one of the co-authors of the Industrial Internet Consortium Security Framework. The framework is based on the IIC reference architecture. The reference architecture is illustrated here. This is not my diagram. This is cut and pasted from the IIC reference architecture document. This is how they think of the world. At the bottom here, I'm going to stop trying to use my pointer. It's advancing my screen. I'll just talk. At the bottom here, we see the control network. It says control, sense, actuate, physical systems. All of that is an industrial control system. Above it, we start seeing layers of other kinds of applications. and the arrows are information flows. Information flows pretty freely inside the control network. But once we get up into the higher levels, we see three kinds of arrows. Green arrows and white arrows are information that's leaving lower levels, that's moving to higher levels, or that's moving around within inside levels. The red arrows are control. Anything that moves into the control network is a control. Every message that enters the control network causes a CPU inside the control critical network to execute instructions that that CPU would not otherwise have executed. Every single message that comes in is controlling that CPU to a degree. And who knows what the consequences of that CPU executing those instructions are. That control may propagate through the entire thing, which is how attacks work. So reference architecture recognizes that control is different from monitoring. What do we do about this? Well, if all we have is a firewall between the layers, what can we do? We open another port. To a man with a hammer, all the world's a nail. To a man with a firewall, all problems are solved by opening another TCP port. Modern practice demands, and this is what's documented in the ISC framework, by the way. Modern practice demands disciplined control. When, not if, when we need to send control information into a more critical network, we need to use the most secure, the safest way that meets the business need, not just whack, open another TCP port, no matter what kind of information, no matter what the business need is. And if I may, all of the offline mechanisms that I talked about earlier, they're all about control as well. The OT test bed is a very important kind of disciplined control. It's offline, it's very slow, but it's as safe as we know how to make it for complex information artifacts coming in. But we're talking about online flows. Let's come back to online flows. How can we discipline those? Here's a classic design. A control network has a lot of equipment in it, including an OPC server on the left. In the center, a historian sits in a DMZ. On the right, we have clients on the enterprise network. The historian sends requests into the OPC server responds. Query response, query response. All of these communications, query response, between the client and the historian, between the historian and the OPC, they're all bidirectional. How can we do this unidirectionally? Well, we put a unidirectional gateway in, and you see that the OPC server in the control system, in the dashed line, has been added to the DMZ. The gateway emulates the OPC server to the DMZ. The software in the gateway, again, the gateways are hardware and software. The hardware is one way. The software, in this case, emulates the server. The software in the gateway sends a request to the OPC system on the left and says, please give me all your tags, all your tags and all your data, all your values. Sends that snapshot out. Now, on the outside, the software is a standard OPC server. The historian queries the server on the DMZ and gets the same answers from the emulated OPC server as the live server would have given. All unidirectionally. What we've done is we've defined the control system as the control critical network. We've unidirectionally connected it to the DMZ. We have disciplined the incoming flow. We used to send queries in. The discipline says you don't need to send queries in. If all the data you need is already on the DMZ, emulating the same system as in the ICS, everything that used to work still works. There's no need to send the queries in. The best discipline is eliminate the inbound flow entirely. And it's possible to do that right here. So, I'm guessing that, some of us have found this concept to be new. Others of us have heard about this before. You've been maybe on one of my webinars before. You may have looked at it a bit. You may have looked at it and looked at your network and concluded it can't possibly work. Well, what's new in the Black Book is a catalog of 20 different network architectures, 20 architectures documenting how different kinds of industrial sites with different kinds of these 20 example networks, the huge variety of ways we could use unidirectional technology. This knowledge used to be walking around in the heads of about 9 people inside a Waterfall. Nobody else knew this, and I thought, this is silly. The world needs this knowledge. And so I wrote it down. The first time this stuff has been documented. But you might have looked at the OPC example and said, you're cheating there. You managed to get rid of the inbound flow entirely. Good for you. Let's look at a more complex example. Even if we cannot use antivirus on some of the very sensitive engineering or OT systems, control systems, we still use antivirus everywhere else. One of the things we learn as OT practitioners is that, some of our systems are special, but most of them are not. The ones that are not special, we put antivirus on. We're going to need antivirus updates, aren't we? They've got to come in somehow. And in batch processes, refineries, even mining, batch processes, we need production orders from the SAP system to tell us what to produce next, what the quality requirements are, and so on. These things have to come in, usually a few times a day. How do we do that? We do it in the red in the center with a reversible unidirectional gateway. Classic unidirectional gateways are one way out, nothing back. No questions, that's it. A reversible gateway can flip over. So it physically looks like a unidirectional gateway. It has only one transmit board, one receive board. It can only send one way, but there's a button on the front. If we press the button, it is as if the system picks up, flips over, and sets down. It can be one way out or one way in, but never both. When it's one way out, we're replicating OPC servers and process historians and such. When it's one way in, the software cannot control the flip. The flip is a hardware function. But the software can sense the flip, and the software can say, oh, look, it's time. It's 2 in the morning. The thing flips for 10 minutes and then flips back. The software says it's time. The software is a client of the antivirus server, logs into the antivirus server, fetches the latest updates, checks the crypto to make sure they're authentic, sends them through and emulates the antivirus server to the industrial control system. Same thing for the SAP server. Pushes, the production order, once we've checked all the crypto, pushes it into the control system, and 10 minutes later, it flips back. That's it. There's no TCP port open constantly that's an opportunity for attackers to test for 0 days. The hardware's flipped back. There's nothing touches the control system until the next update. And when that update occurs, it is clients on the IT network, on the enterprise network, fetching data. It's not a router sitting there, trying to filter packets, trying to figure out the difference between good and bad packets. Good luck. There's no algorithm that can do that. So here's an example. The bottom line is, again, we've defined the control system as a control critical network, and we've deployed a reversible unidirectional gateway at the boundary there. Where are we? I've lost track of myself. Okay. Here is my last example. Something that we've seen in about the last 18 months is this pattern of communications. Anyone's been watching the industrial security space knows that in the last 18, 24 months, there's been a lot of venture money dropped on OT intrusion detection startups. There's some real progress being made in recognizing industrial protocols, in analyzing them, in developing anomaly detection for what's normal, learning algorithms, artificial intelligence. All this stuff, all this innovation is being applied to the job of producing a sensor that will watch the packets on an industrial network and diagnose potential attacks. The problem is that if we connect that sensor, the problem is that we need to connect that sensor to a mirror port. And we have 2 choices. We can put the sensor on the industrial network, or we can put it on the IT network. If we put the sensor, the physical machine that is running the software or the virtual machine on the industrial network, the problem with these sensors is that from time to time, they have false alarms. This is the nature of intrusion detection sensors. This is why people in the Security Operations Center need to log into these sensors from time to time to tune them, or to update them, or to put new signatures into them. If we have the intrusion sensor on the industrial network, all of those people need to be able to log into all of the operations networks in all of our plants. Can you imagine every one of your plants going there and trying to explain, I have 73 people in my enterprise SOC, all of whom need to log into your control network? They're going to be asking, who are these people? What are they doing on my network? What are they doing it to on my network? What are the consequences of giving 73 people remote access to my control critical network with truly unacceptable physical consequences of misoperation, much less compromise? They're going to resist. The place for that sensor is on the IT network, where the operations people, or the security operations people, can get to it easily. The problem is that now we've connected mirror ports on control system switches into a sensor on the IT network. These mirror ports are notoriously bidirectional. The vendors, the switch vendors, will tell you they're unidirectional, and then they'll contradict themselves a paragraph later. People who test these things will say, no, they're not unidirectional. Or if they are unidirectional, they're software unidirectional. You know, exploit a zero-day, or worse, just steal a password. You can reconfigure them, and now they're not bidirectional, and now you've got a path back into the industrial network. Throw a unidirectional gateway in there. Emulate the mirror ports to the intrusion sensor on the IT network. And you've got the benefits of monitoring the OT traffic from the IT network perfectly safely in a way that the security operations people can reach in and manage those assets easily and securely. In fact, you know, this is such an important application. There's so much attention in the last 24 months being given to finally bringing operations networks into the enterprise security monitoring fold. We wrote a whole ebook on this. It's on the website. If you go to waterfall-security.com/gold-standard, the new gold standard for how to do safe OT security monitoring, you'll find the ebook. I'm coming up on the end here. A word about Waterfall, if you'll indulge me. We are the OT security company. We've been doing this for 12 years. We enable secure operations. We prevent remote attacks, online attacks. We protect industrial networks. We protect enterprise engineering networks. We protect OT networks. We protect physically mission-critical environments. We see our products used all over the world in OT environments to do safe integration of OT networks with external networks, usually with enterprise networks, but we occasionally see people go from the OT network straight out to the internet. Why? Because when you put a unidirectional gateway in there, it's safe. It's physically impossible for any attack, no matter how sophisticated, no matter how militarily sophisticated, to come through the internet and compromise the physical protection of the gateway. Disciplined control is the third principle here. We do not bang open another TCP port. When we are presented with a network with a set of business needs and communications needs, we develop the strongest solution that meets the need. The strongest solution that gives us the business benefit, and the most specific solution to provide that strength. We hope that we are defining the high end of IT security, or of operations security, by documenting these practices of thoroughly secured site and applying these practices and developing the technology to support these practices routinely. That's what I had for you. In short, in summary, attack capabilities only become more severe over time. Attack tools become more capable. All of us respond by increasing the strength of our security postures. The entire bell curve of security strength needs to move to the right. The problem is we see too many organizations stalled on their OT security initiatives because of resistance from operations. The time has come to start making progress. We need to recognize that physical engineering risks are different from informational business risks that enterprise programs address. We need to negotiate with operations, with the engineers. We need to sit down and figure out which assets to microsegment, which assets to model as engineering assets, and we need the engineering assets to be thoroughly protected using a robust, disciplined, SecOT approach. We need to bring everything into the enterprise security fold with as little deviation from corporate standards as possible. With engineering safety and engineering protection needs addressed, we can start seeing progress. We can start seeing progress instead of conflict and paralysis. The book here is available on Amazon, but Waterfall, as a public service, is making free copies of the book available for a period of time. Go to the URL that you see on the bottom here, waterfall-security.com/sec-ot. Give us your shipping address, and we will try very hard. I mean, we occasionally have trouble with customs, but we will try very hard to get a book into your hands. No charge. And if you want to give me feedback on this, I'm very much open to feedback. As I said, people have mixed reactions to this. I can only get better at documenting, what people are doing and, the right way forward if I get feedback from the people who are using the knowledge, who are reading the knowledge. Tell me what you think, good, bad, or ugly, and I will try to get better next time. One last thought for you. We've been running the Industrial Security Podcast for 6 months now. We have a new episode every 2 weeks. We have guests from all over the industrial space. We have vendors, we have government agencies, we have owners and operators. We have others. We have recruiters. We have board members from power companies talking about governance issues. The podcast is not about Waterfall. Waterfall is a sponsor. We produce it as a public service. The podcast is all about our expert guests. If you like it, submit a review, spread the word. You can see it at waterfall-security.com/podcasts. You can go on your favorite podcast apps on your phone, subscribe to, and search for Industrial Security. You'll find it, see the logo, sign up, and you'll get notifications when new episodes come out. That's what I had. Thank you so much for listening. Derek, do we have questions back up here?
We do, in fact. So if you want to advance it to the next slide.
Oh, there we go. Sorry, I'm on the end of mine.
Okay, wait. I may
be. You want to take over the presenter again?
Yep. I can do that. Change presenter. Hold on, everyone. Okay. And I assume you can see. Oh, yep, there's your podcast. Okay, so you keep sending questions in if you have them. So yeah, I'll just switch back for now to the podcast page that Andrew shared. Thank you, Andrew. You got some feedback, by the way, besides questions that people found the information very useful, and thanking you for sharing it. First question, does the Unidirectional Gateway work with Ethernet communications bi-directional requirements?
The gateway is a hardware device. It's got no CPU. It's got no MAC address. It has no IP address. It forwards Ethernet frames, but those frames, again, inside of in the NIST definition, a gateway is both hardware and software. The hardware component, the CPU-less component, is connected to a host. It's not connected to a network, and that host is sending information into the hardware. On the other side, the host is receiving information. The software in the host is being the client and replicating the servers. And so no Ethernet frame from a network makes its way through to the other network. The clients are managing communications with servers on each side. The one exception is the mirror port. When a mirror port comes in, we do emulate that mirror port faithfully, meaning the packets that come out the other side look just like the packets that come in. But again, they're wired directly into a intrusion detection sensor that's consuming the packets and not sending anything back. And even if they did, it'd be pointless. Nothing gets back. So I think the answer is yes, we forward Ethernet stuff, but the longer answer is the software does the interface to the networks. And no, nothing ever gets back from the outside, back through the gateway to the inside. I hope that answers the question.
And let me know, Dennis, if that does answer your question. What's to prevent hackers from waiting for the gateway to reverse and penetrate the ICS?
What's the advantage, or what? Okay, say the question again slowly.
What is to prevent hackers from waiting for the gateway to reverse and then penetrating the ICS?
That is possible in theory, but first you would have to take over the host on the outside. Again, because if you have a presence on the network on the outside, on the enterprise network, none of those packets are forwarded through to the other side. The host is a client. The host is like a spreadsheet. You send a packet to a spreadsheet that it doesn't expect. You send a connect request to hackersrus.com, port 80. What happens? The spreadsheet says, I'm not a web server. I'm not hackersrus.com. I'm not a router. I have no idea what to do with this packet. You send a packet like that to a firewall, and it's going to apply the rules. And if you can find a way to get that packet, sneak it through the rules, well, you're attacking a system right through the firewall. You send that to a spreadsheet, it's going to throw the packet out because it truly has no idea what to do with this packet. The same is true of the gateway software. So, you've got a multi-step process if you want to get through. You got to take over the device on the inside. Now you've got to find one of the weird waterfall packets that's going to make it through, because our protocol is not the same as the internet protocol. We don't use internet protocol through our device. And on the other side, even if you manage through some heroic effort to find 0 day after 0 day and work your way through and get some kind of foothold on the inside network, well, now you're flying blind because nothing's coming back, is it? You're one way in, nothing comes out. And then the device flips over and you can't send command in anymore and you're stuck. So the message here is that the flip is much stronger than a firewall. Nothing, first law of SCADA security, nothing is secure. I'm not saying buy a flip or buy a gateway and put your feet up and you're done. I'm saying we have a solution that is much stronger than firewalls, and so thoroughly secured sites use that solution in preference to firewalls when they need to send antivirus or other disciplined, scheduled updates into a system. I hope that works.
Thanks, Andrew. You mentioned there is no algorithm to recognize good versus bad packets. However, in other industries, I've experienced successful software-based microsegmentation strategies aimed at reducing lateral movement of bad actors through fine-grained security policies. Do you see the need for OT to have both a hardware-based unidirectional gateway as well as software-based microsegmentation solution? What are the potential pros and cons of either or, and could they complement each other?
The short answer is that they generally complement each other. We have to be careful about using, the new buzzword is zero trust, which means a lot of crypto. You got to be careful about using crypto on some of the most sensitive OT networks. But beyond that, use it wherever it makes sense. You use all of the enterprise security knowledge and experience and practices wherever they make sense. We make exceptions where we are forced to because of the physical consequences, because of the nature of the engineering and the control networks. We make exceptions where we need to. We weaken the enterprise security posture where we must in order to protect physical safety and physical operations and physical equipment. And then we add SecOT as a layer around it. So yes, absolutely. We use everything that makes sense. These robust sites, the most secure sites, they don't put, a gateway in and put their feet up, as I said. They apply all of the best practices. They make the exceptions that they're forced to, and then they add SecOT as a robust extra layer that addresses the residual vulnerabilities that were introduced by the exceptions that had to be made, that they were forced to make, and B, dramatically increases the strength of the perimeter to further protect from, again, what are truly unacceptable physical consequences, running from downtime for a $100 million or $1 billion process to, as I said, human casualties and worse.
Thank you, Ginter. You said that that IT taking responsibility for cybersecurity in OT environments, is this a direction you recommend, or just the way things are going? And I'm particularly interested in this. I get drawn into this conversation on panels and in various companies and see a lot of different things. But it's interesting if you could share what you're seeing, if any, at a macro level. You know, is there a trending? It's clearly being done in individual cases or places in different ways. But yeah, what are you seeing for IT taking responsibility in OT environments?
So let me give you a medium-long answer to that. Experts disagree. In my first book, the Red Book, I documented what I thought people ought to do. And the reaction I had, and this is the reason I ask for feedback. I really do want feedback. The feedback I got for the Red Book varied from Andrew, I disagree so fundamentally I could not finish reading this, to the other end of the spectrum where people told me, experts on both sides told me, Andrew, what you've written is so obviously true, I don't know why you bothered to write it down. There is enormous disagreement in this space. So I took a position with the Red Book. With the Black Book, what I've done instead is say, you know, debate doesn't seem to be helping here. I'm going to document what I see as successful, thoroughly secured sites do. First they do this, then they do that, then they do the next. There's no controversy there. You can decide for yourself if you want to apply these practices, but there's no arguing with what these practices are. This is what the world's most secure sites do. If you want to be like them, this is what they do. You choose. Now, what I observe is that, you know, in the last, we sell to people in this space. What we've observed in the last 18, 24 months is that historically IT has been sitting at the table, but has not been calling the shots. In the last 18 to 24 months, we've observed that in the engagements we've been in, increasingly, dramatically increasingly, IT is calling the shots. I don't know why. I'm not an industry analyst. You might want to ask Gartner or ARC or one of these industry analysts what's going on. This is what we observe. This is the reality. You can debate whether it's good or bad. It is what we see happening.
Thank you, Andrew. Yep, that is a super fascinating topic. We may have to organize a panel just around that topic alone. You said that attacks on operation technology are growing in frequency and impact. Where can we find out more about these? Attacks on IT are often in the news, but OT not so much.
Yeah, I mean, when I say the impact's increasing, I'm referring to the news we've all heard about. You know, Stuxnet was the big news, you know, in the day, and then things kind of quieted down. But, you know, lately we've seen, I don't know, there was the steel mill incident. There's the attack on safety systems where the consequence wasn't realized, but there was a real threat to human life at the plant. We've seen, you know, ransomware take down, you know, a number of plants. I think it was like 6 plants at a time at Norsk Hydro. We've seen manufacturing sites. I think it was in the news that a Honda plant went down. They lost a day's production. They were behind for their quarter 1,000 vehicles. Why? Because that plant was running flat out, and you can't recover the 1,000 vehicles it would have produced. So this is all just in the news. I don't have secret sources that I'm referring to. This is public knowledge.
Thank you, Andrew. Hey, what about WANs, wide area networks, and how does the unidirectional gateway technology work within the WAN environment?
So by WAN, I assume you're meaning stuff like the WAN that's reaching out to pumping stations on pipelines, or that's reaching out to substations in the electric grid, where we have sensors, actuators, devices, and physical equipment that is physically distant. And you know, that's a unique problem. The WAN is intrinsically part of the control system, yet it's outside of our control in terms of physical perimeter. You can't put a fence around the United States. Well, maybe you can. But you can't put a fence around the electric grid. You can put a fence around the substation, but not around the entire grid. It makes no sense. And so I do actually have a network diagram in the book that describes that. It's a little complicated. Let me give you a simpler answer. what we see happening sort of as a trend, increasing fairly dramatically, is that power utilities, electric utilities, with their substations, they're not doing the complex diagramming, I forget which network architecture in chapter 6, for full unidirectional control of the substation. What they're doing increasingly, this is the trend, is putting unidirectional gateways onto the small networks in the substations that contain the protective relays. Because they've said, look, if the lights go out, well, that's a business consequence, it's a physical consequence, but we can turn them on. We'll restore the equipment from backup, or we'll drive out to the substation and physically turn the power back on if there's a Ukraine-style compromise. If the lights go out, we can turn them on in a matter of minutes or hours. We can do this. But if the transformers burn out because someone has tampered with the relays, it's going to be weeks or months before those things are replaced. There is no worldwide inventory of high voltage transformers. And so what we see them doing is they're defining the relay networks as control critical. They're saying the other ones are not yet important enough, or maybe what they're doing, maybe their strategy is start with the most important networks, protect it unidirectionally, get some experience with the technology, and maybe in the future expand. But what we see them doing, definitely as a trend, is deploying unidirectional gateway technology to protect the 10, 20, 50 relays in high voltage substations, so that if the lights go out, if due to a compromise, they will come on again a couple hours later because all of the equipment has been protected. So that's the trend we see there. But there's more complicated scenarios in the black book if you want to read it. There's a reason to order a copy of the black book if you want a detailed answer to that question.
Well, thank you, Andrew Ginter, again from Waterfall, one of the very first and most reliable supporters for the CCA organization, and we thank you on behalf of all the members. I'd like to say thanks again. Thank you for sharing all the information today, and this webcast will be available in the CCA portal, where we put all the virtual meetings and webcasts that we do for access over time. So please feel free to refer back to that if there's something in Andrew's presentation that you would like to utilize or take a look at. Again, it'll be there for you in short time frame here. Again, we have our next session coming on October 31st, and we hope that you can attend that. I've left that slide up for a little while, and you can find registration again on cs2ai.org. With that, we will conclude our October 3rd webcast with Andrew Ginter.
Thank you very much. And thank you to all of our listeners.